Okay, hello everybody and welcome to the GCSE and A-Level Physics live stream. This one is the second one I've done. It's the 16th of April today, and we're going to be doing GCSE from 7:30 till 8 o'clock, and then from 8 till about 8:30 I'm going to be doing A-Level. So it's basically going to be one stream that everybody can join. I would love it if you haven't already done so to make sure that you do like the video. There's a little heart thing that you can kind of tap on if you're watching this live as well. And of course, as we go on, you might see that my eyes keep kind of going away from the camera, and that's really because I'm just looking at the comments. So I will be reading the comments and answering as many of them as I can. So it's great to see so many people here already. In the chat, if you are watching, do let me know if you are doing GCSE, and if so, which exam board you're doing. If you're doing AQA, OCR, EdXL, SIA, CCEA, whatever it might be, or if you're doing A-Level, and again, which exam board you're doing. Right, in terms of the content, I'm not doing it in a specific order, but what I am doing is I'm basing it on some papers I've written. So for GCSE, I have these practice papers, and basically what I have is 12 papers in total, and my kind of plan is that this week I'm going to be doing a bit of paper 1 and a bit of paper 2, and I'm going to basically be doing stuff from alpha, and then as the weeks go on I'm going to be doing some stuff from beta, gamma, delta, epsilon and zeta. So that's kind of my rough order. For people doing AQA, GCSE, triple science, sometimes called separate science or just physics, these are ideal for that. So I know there's over 100,000 people doing this paper, and if you're wanting to get to the highest grades, to go from like a 7 to an 8 to a 9, then you should really maybe consider buying one of these. And of course, as you go through it, you'll see that if you do each of the papers, or even if you just buy the exam pack and then maybe look at topics that you're not so familiar with, you can identify which question in which paper has these topics in. So today we're going to do a little bit more about resistors and series and parallel, and then we're going to be looking at, I think it's a question from paper 2. We're going to be looking at, I can't remember what I've said now, but if you ever want to find out what I'm doing, I do have a schedule, and in the description beneath the live stream you'll see that there's a link to GCSE Physics Online, and then there's a page here called Live. So you can just click on that red icon there, and this will take you to this page here. So this is something that I've been working on today, and basically there's this kind of timetable of what's going to be coming up over the next few months. If I just zoom in on this a little bit. So we've got April, May and June. The greyed out ones that just haven't been kind of planned and put on the website yet. You can click on the date. So today is the 16th. If you click on that, it brings up, you can just about see that. It brings up the questions that we're going to be doing and from which exam paper they're from. Okay, so basically you can find out the topics that we're doing over the next few days. So we're going to be looking at energy and specific heat capacity tomorrow, and then sound waves and forces on Thursday night. So you can find all of that at gcsephysicsonline.com/live. Now, I did have another question based on what we did yesterday. Yesterday, I showed a lot of people this kind of revision guide that I made for AQA GCSE Physics. Now, it's a completely free download, and basically what I have within this guide is some stuff which is specific to AQA. So that's people like Nathan, Jojo, people like that who are kind of in the chat at the moment. This is ideal for you. There's also a bit about how to revise, and I think what I did here as well was I had a list of some of my GCSE videos. So if you are revising and there's a question that you don't understand, or a bit of the course that you can't remember being taught, or maybe you're absent that day, I have videos where I explain everything and give worked examples for the entire GCSE course. So these are videos for GCSE Physics. I've got some more here, so you can see that there's a huge amount, and all of these are organised on the website. Within the guide itself, it has all the topics that come up, and then I've used the AQA material, and I've basically made this into a checklist for you to kind of tick off as you've revised it. So by working through this methodically, and this has got more stuff than the actual GCSE specification, then you can basically tick off everything that you've revised. And this is also really good for those doing combined science. So the stuff that is only being done by people doing triple science has got a blue bit by the side of it. Everything else, which is just a kind of a normal box, is for combined trilogy for AQA. Okay, so Syrupy Gaming, yeah, this is perfect for anybody doing trilogy as well, so everybody has to know this content, but for those doing triple science, there's a couple of extra little bits. Also in the back, there's, again, loads more information, how to use past papers. There's also some of the definitions that you need to know, so these are things that everybody watching this should know off by heart. So if you're watching this stream, if you're doing A-level physics, you should definitely remember these. If you're doing GCSE, you should know how to define Newton's third law or how to define stopping distance. So yeah, this is something that if you want to get hold of it, it's really easy to do. So you can download it tonight. All you need to do is if you go to my GCSE Physics Online website, if you go to Home, that allows you to select the exam board that you're doing. And because this guide was written for AQA, if you click on AQA, it will take you to the big AQA page. And it's this thing here. It says AQA GCSE Physics Revision Guide, free digital download. If you click on that link, it'll take you to a page. You then just need to put in your email address and I'll just email it out to you. And also, that will add you to my newsletter, which I send out once a week. And of course, if you don't want to be informed about what's happening, then you can always unsubscribe from that. Right. A couple of questions that people have said. So I've got a good one from physics. I like that. They're doing triple science. Any tips on how to memorise equations and mainly how to apply them to questions? I think the best way to do that is just do as many questions as possible. So doing as many past exam paper questions and also like the kind of practice questions I've written as well. But basically by doing this again and again and again, you will have your data sheet that has equations on it for the exam. But really, that should just be to double check that you know what that you've written down is actually correct. But I mean, you can just kind of try and memorise that data sheet. But I think the best way to know which equations to put down and the best way to become familiar with them is just to do as many questions as possible. Do I have any tips on how to retain all the knowledge in the last 3 weeks? Basically, you've still got over 3 weeks till your exam. I think you've got over a month until your first physics exam, and all of you watching this can make a massive change because you get really focused and there's a point where you're doing lots of work and it suddenly just kind of clicks. Okay, so let's have a look at a question that I didn't quite get time to do yesterday. So this is from my physics paper 1 alpha, and it's a question that will continue, but you don't need to know the previous bit. So basically a question about resistors. So, basically the teacher carried out their own investigation, but before they started the experiment, they noticed that the ammeter reading was 0.15 when the ammeter was not connected in the circuit. And the first thing we need to do is state the type of error this is. So again, if you're watching this live, then I am watching the chat. If you know what the answer might be, if you want to, it doesn't matter if you get it wrong, just put it in the chat. State the type of error. Well, basically, even though there's nothing being recorded, we're still getting a reading. And this is due to maybe the calibration of that instrument. Maybe it's not particularly accurate. And this one here, Leon, is the first person I've seen it, is a 0 error. Okay. Now, this is something that I noticed this morning when I weighed myself. And basically, when I stood on when I put the kind of weighing scales down to actually see how much my mass was, basically there is like a dial, and there's like a kind of a number line here, and then the dial kind of points to whatever the number is. Now, this morning, that was like 0, 1, 2, 3. So before I even stepped on it, this was reading about between 1 and 2. So even though there was nothing on it, it still gave a reading of 1.5 kilograms. Okay, and what you might notice if you've seen these kind of bathroom scales, there's often like a little dial at the top, and you can basically just rotate that dial around, and that then resets it back to 0. Because what you want is like basically something like this. So you've got the 0 at the dial when nothing's on it. Otherwise, what you'd have to do is if you took a reading and maybe the reading that you took was 92 kilograms, if you hadn't zeroed it beforehand, it already read 1.5 beforehand, you stepped on it, it read 92, the actual reading should really be 90.5 kilograms. Okay, so yeah, 0 error. It is kind of a systematic error because it would lead to a systematic error in all of your readings. But yeah, right. Oh, cool. So I'm just sort of seeing some of the kind of chat here. Yeah, loads of people getting the right answer, which is brilliant. Yeah, somebody saw my Olympiad video and found me from there. Hello, yeah, it was great to go to Oxford over the Easter holidays and actually meet some of the people there. It's brilliant. Right, the next question, it is in a GCSE physics paper, but all of you can answer this because this is just a maths question. Okay, ignore references to resistors. The question says, find the value of the resistance recorded in experiment 4. So what we have is an unknown value here, which I'm just going to call R, or I'm going to call it R with a question mark. So this is our unknown value. And basically the mean value is 13, but we had readings of 11, 14, 13 and 12. Now, of course, the mean is one of the averages that we use in GCSE physics. I'd say it's probably used 99% of the time. You do need to be aware of the median. You do need to be aware of the mode. But in terms of actual scientific experiments, calculating the mean is the most important average. Okay. Now, lots of people there are getting 15, and the answer is 15. Now, in the exam, if you are bold enough and you just write down the answer and it's correct, and the answer is correct, then you would get 2 marks. However, what I think you should always do is you need to show your working out. And the reason for that is if you did make a mistake, then you could still get maybe 1 out of the 2 marks. Okay, now the first thing is to work out the mean, and we know the mean here is equal to 13. That's equal to all of these numbers added together. So we've got 11 plus 14 plus 13 plus our unknown value of resistance plus 12 divided by the total number, which is 5. And if you then think about that, we could basically say that that plus that plus that plus that is 50. So we can say that 13 is equal to 50 plus R divided by 5. Okay, if I multiply both sides by 5, we can say that 13 times 5 is equal to 50 plus R. Now, 13 times 5 is going to be 50, 65. So 65 is equal to 50 plus R. So 65 minus 50 is equal to R, which equals 15. Okay, so that's one way of doing it, and I can see lots of people are doing it there. The other way that you could do it is think, well, okay, if the mean is 13 and that one's 13, we're going to kind of ignore that. We then have a 12, which is 1 below that, and a 14, which is 1 above it. So the mean of 12 and 14 is just 13. And now we've got something 2 below it, which is 11. So we need to have a number which is 2 above it, which would be 15. Okay, so that's a kind of other kind of logical way of thinking about it. Right. Now the last bit, I hope this doesn't confuse too many people, but I have seen lots of teachers teaching this incorrectly. Okay, and it's about Ohm's law and referring to the equation V equals IR. And they say that, or they refer to this as Ohm's law. This is not Ohm's law. Okay, and the reason for that is that V equals IR is always true. So you could look at a diode, or you could look at a thermistor, and if you know V and I, you could use that to calculate R. In actual fact, this equation, I think the best way this can be written, and this is still GCSE at the moment. Do I have a website? Yes, I do. My website is physicsonline.com, or all the stuff today is on gcsephysicsonline.com. Everything is there. Okay, I think that a better way to write this equation is to say that R is equal to V over I. Okay, now this is really what we mean by the resistance. The resistance of an electrical component is defined as the ratio of the potential difference across it to the current through it. Now that is always going to be true. Okay, so this is always true. Ohm's law, on the other hand, basically says that for a component, the potential difference is going to be proportional to the current at a constant T. Okay, so excuse my shorthand. So at the moment, V is proportional to I at a constant temperature. Now this is what Ohm's law says, and it only applies to certain components. Now the main thing that this applies to is if you have maybe a resistor. Now the whole point in a resistor is it has a constant resistance, or sometimes you might just have a piece of wire. And if you look at the relationship between the current and the potential difference for a piece of wire, then the two things are going to be proportional to each other, provided we have a constant temperature. Okay, now that is Ohm's law, but that's not necessarily this. Okay, now the reason for that is if you had a component like maybe a filament lamp, if we were to look at the IV characteristics, and this is an experiment that a lot of you will have done before, we basically find that we have this kind of almost like an S-shaped curve. Now, on this graph here, just let me know in the comments, is I proportional to V? So, looking at this line here, is the current proportional to the potential difference? Okay, let me know what you think. And I can see that some people have got exams soon, so good luck if you've got an exam quite soon. Okay, no, free maths lessons. Taking on the big dog free science lessons. No, yes. So this here is not an ohmic conductor. And therefore, this component, the filament lamp, does not obey Ohm's law. However, if you wanted to find out the resistance at any point, all you need to do is read off maybe the value of current and the value of potential difference. Time Lord, thank you so much. I really appreciate that. Thank you for that donation. Time Lord, let me just put that up at the top. I'm just going to pin that. Can I pin that as a comment at the top? Maybe not. But yeah, thanks so much for that. And thanks for everybody else liking that. Sorry, it's just kind of put some stuff in the chat, which is brilliant. Right, this is not an ohmic conductor and I is not proportional to V. But if you wanted to work out the resistance, then you would take a value of I and a value of R, and then R is equal to V over I for that particular instance. In actual fact, wherever you look along this line, V is equal to I times R. But of course, the difficulty with something like this is that R is not constant, and that's why V is not proportional to I. So we can't say V is proportional to I because the resistance is changing. So that is always true, but in this case, I is not proportional to V. Hopefully that makes sense. Right, if you do get stuck, I do have another video where I explain that again over at GCSE Physics Online. Right, so the next question then is one to do with motion. So for something like this, I'm just going to go through the kind of best practice. Now, if you follow this method, you will always get the right answer. The first thing is maybe just to read the whole question before you start working it out. So we've got a basketball player dribbling towards the net at 4.2 meters per second for 2 seconds. Calculate how far they travel in this time. So read the whole question. Then what you want to do is maybe underline certain things. And so I've underlined some numbers. I'm going to put like a symbol next to it. So 4.2 meters per second, well, that's going to be their velocity or their speed. I say velocity because it's given us as a plus. The time is 2 seconds, t. How far do they travel? Well, that distance is s. Okay, so we've identified the numbers, we've identified the units, and the next thing is we just need to think about an appropriate calculation. Now, of course, I would probably remember this, that s is equal to vt, or you might remember this as the speed is equal to the distance divided by the time. Okay, so we've got the equation we're going to be using. We then have, we've already identified what these are up here. And if you're not sure, it's always just worth checking in your equation sheet. It doesn't take very long to do. So S equals VT. We're going to put the numbers in. S is equal to 4.2 times 2 seconds, which is equal to 8.4. Don't need a calculator. And therefore they travel 8.4 meters in that time. Okay, hopefully that's all good. Does that make sense, everybody? Oh, so I'm doing, so the chat's just gone a bit weird. Okay, right. They come to a stop in a time of 0.2 seconds. Okay, they come to a stop. I'm going to put that down there, and I'm going to say that V is equal to 0, and that's our T. Okay, calculate the acceleration of the player with an appropriate unit. So 4 marks available. If we're looking at acceleration, we can just do the unit straight off. The unit for acceleration, if everybody just wants to put it in the chat, what is the unit that we use for acceleration? Easy marks, but I'm sure there'll be people who kind of miss that out in the real exams. But we're trying to calculate the acceleration. Okay, how do we do that? Well, the acceleration is equal to the change in velocity divided by the time. Yeah, meter per second squared. Okay, excellent stuff. All of you have got 1 easy mark in the exam, which is brilliant. Now, do we know their final velocity? Yes, because they come to a stop. So their final velocity is 0. Do we know the initial velocity they were going at? Well, actually we do. And it was in a previous part of the question. So don't forget what was up in a previous part, which might be used later on in that question. So the initial velocity, the speed that they were going at, their original velocity was 4.2 meters per second. So you've got 0 minus 4.2. The time it took was 0.20 seconds. So we've basically got minus 4.2 over 0.20, which is the same as 42 over 2.0, which is equal to minus 21. And so the answer for this, as Anissa just said there, excellent work, is minus 21 meters per second squared. Okay, so Humphrey, excellent, you got the minus sign in there. You're going to get a mark for the magnitude of 21. You're going to get a mark for meters per second squared. You're going to get a mark for the correct working out and the correct equation. And also, Nathan, I can see you've just retracted your message. Don't worry about it. You also get a mark for the minus thing. And I reckon that most people will have forgotten to put a minus sign in. So because it's an acceleration, but they're slowing down, it's going to have a negative value. And that's because acceleration is a vector quantity. Right. We now have a bit of multiple choice. Again, play along at home. This is still GCSE for another 7 minutes, just while I'm doing this stream. So they throw the ball upwards towards the hoop. Identify by circling the letter which of the following velocity time graphs shows the vertical motion of the ball as it travels up to its highest point. So this is a difficult question. Anybody who's going to join in for the A-level thing might not get the answer either. So I think this is like a grade 9 level question. Okay, so what are people thinking? We've got somebody saying B. Okay, we've got somebody saying A, D. Okay, this is like the kind of thing that gets you those kind of top marks. It's not easy. It looks like a simple question. We've got people saying A, D, B. Okay, so let's just think about it, right? So if you're throwing a ball up into the air, okay, so you've got this ball. I don't actually have one here, but basically it starts off quite quickly, and as it goes higher and higher, it slows down till it gets to a stop at the highest point. So basically, the ball starts off quick and then it slows down. Now it can't be C because on this velocity time graph, it's going at a constant velocity. So if you know it's definitely not the right answer, just get rid of it. And that will help you, rather than it being a 1 in 4 choice, you then have a 1 in 3 choice. Okay, now this one here, we've got a low velocity that increases. So we've basically got something accelerating with a constant uniform acceleration, but it's getting quicker and quicker. And we're looking at the vertical motion as it travels up to its highest point. So it can't be getting quicker, so it can't be A. Now, we've now got a 50-50 choice. Is it B or D? And I can see in the chat, we've got Ben says B, Humphrey says B. Yeah, loads of people are saying B now. Lots of people are saying D. Now, as it's going higher and higher, there's going to be a downwards force acting on the ball, and there's going to be a constant downwards force due to its weight, which is the force which is acting downwards, even though it's going upwards. And that means it's going to get slower and slower and slower as time goes on. And for that reason, the answer is B. In actual fact, if you were to calculate the gradient, we'd find that basically we have this kind of uniform acceleration or uniform deceleration, and actually the value of that would be about minus 9.8 meters per second squared, because we've got gravity acting down, and therefore there's this weight force acting down, and therefore we have this uniform deceleration. So the higher it goes, the slower it gets till it gets to 0. This one over here, it kind of starts at the high velocity, it ends at 0, but this is basically something that goes up at like a uniform speed and then stops. That's almost like, imagine a lift going up a building. So it kind of goes up at a fairly uniform speed, and then it slows down really quickly at the end. And a ball doesn't go up and up and up and then stop. It kind of goes up and slows down as it does that. Okay, yeah, hopefully that's all right. Right, for 1.4, we've now got an instant when the basketball is travelling horizontally. Draw arrows to show the force or forces acting on the basketball as it travels through the air. So if it's going through the air, what forces are acting on it? So in the, and yeah, that last question, by the way, was tricky. That's like a grade 9 question. So what forces are acting on the ball? Let me know what they are. So we've got a small arrow going left, air resistance. Somebody said we've got weight, free maths lessons. Yeah, so we've got 2 forces, okay? We've got air resistance and weight. So, first of all, from the centre of the ball, I'm going to use a ruler, because we always draw arrows with a ruler when we're drawing vector things, okay? And ideally you should do this in pencil. To make it clearer for this, I'm going to draw in pen. Now, the actual size doesn't matter too much, but we've got a downwards arrow. Now that arrow going down, right, you need to have a word with yourself if you're using the word gravity. I'm going to call this weight. So weight is the force on this object due to the gravitational attraction of the Earth. So I believe that weight is the best way to identify this. Okay, not mass, not gravity, weight. Okay, I would say that if you said anything other than weight, if you were one of my students at school, then I wouldn't give you the mark. Okay, now we've got a vertical downwards force there. Now, if it's moving to the right, there's going to be another force which is opposing the motion, and that's going to be acting to the left. I'm just going to put that acting from the centre. Again, the actual length of the arrow doesn't really matter too much because we don't have enough information for that. And this arrow here is going to be at 90 degrees, because if it's going to the right and the weight is down, this force is going to be going to the left, because this must be opposing the direction of motion. And for this, you could say drag, or you could say air resistance. Okay, now those, or you could say friction. Actually, I think friction is good, but I think we tend to refer to friction as being due to the interaction when you've got like 2 solids. So there is this kind of frictional drag force, but I reckon friction is often better to describe maybe 2 solids acting against each other, whereas on this, I think drag or air resistance is the better one. So these are the 2 forces. So you get a mark for weight and a mark for this. There are no other forces There's nothing driving it forwards. So hopefully that makes sense. Right, so I think we'll leave it there for the GCSE questions. Someone's asking, why can't you say gravity? I mean, I think gravity is good, but weight is better. Okay, if somebody said mg, which is like the mass times the gravitational field strength to make weight, I mean, again, that's fine, but I would say at GCSE, call it weight. Okay, and that's just the best way to do it. Okay, hopefully that's warmed up some of the people here who've just joined for A-level. So it is 8 o'clock. I'm going to try and stick to the timings. If you've not already seen what I'm doing, then tomorrow, I'm just going to put that over there. I'm just going to go back here. So tomorrow the plan is, and you can find this if you go to GCSE Physics Online, click on live, you can just select the date here or just scroll down a bit. And tomorrow on the 17th, we're going to be looking at energy and also specific heat capacity. And the questions are going to be from my paper 1 alpha. We're going to do questions 4 and 5 in the stream. And of course, if you want to download that question paper, you can just buy it in my shop. Do it tonight. It's worth it. Just get all of them. Everybody, please do this. And that means you've got everything for all of my live streams. And I guarantee if you do all of that work, you will get a really high grade. Okay, so hello everybody doing A-level physics. Tonight, again, if you go to alevelphysicsonline.com and you look at this live icon in the corner, it brings you to this page. This is kind of my plan here, so you can have a look at it in your own time. But basically, I've got a couple of things. I'm going to add more dates as I kind of plan more live streams. But you can scroll down, and today we're going to be doing a question about a pendulum practical simple harmonic motion. Now this is a question, and again, this is a shameless plug because I'm live streaming completely for free, but in order for me to do this, it's really great if you can buy things, which again, I think can really help you kind of get the highest grades. This is my book. This is book 4 from my daily workout series. If you're in year 12, you should definitely buy this and work through it towards the end of this year and over the summer. If you're year 13, it might be a little bit late, but what I have done is on my website, you can download just the questions. So where it says download, if you click on that, you can then download the questions for the stream. So if you haven't already done so, you can download the questions. You can have a work through this if you want to, or you can always, in the future, have a look at stuff before I actually do the stream. So that is what we're doing today. Where are we? There we go. This one. Yeah. So, and also there's a link here if you want to buy the book or you want to watch the stream again. Okay. So this question I think is a nice one. It is not exam board specific, although if you are doing AQA, then you need to know and remember this equation. I think it's given to you in your formula book anyway, but this is the SHM equation for a simple pendulum. And when we talk about a simple pendulum, what we mean is one where the angle that it oscillates through is quite small. If the angle is quite small, we use a small angle approximation for sine theta, and we come up with this equation over here. Right. So, yeah, so I'm just seeing some of the comments. Somebody says, and this is a really good one, I think probably lots of people are in the same position. A says, I've gone through all the content, but I'm still not getting the exam questions. What should I do? I think probably 90% of the other people watching this stream, most people will have finished most of the content, but sometimes they just don't get it. And that's absolutely fine. And you've got to remember, you still have a long time before your real exams. And in that time, you will make massive improvements. What you need to do is just do as many exam style questions as possible. And as you do that, it's going to be the best way to do like spaced repetition, because it's going to be kind of giving you lots of different questions to do on lots of different topics. There's going to be this kind of a huge amount of work where you're really having to think about it. And then you can always go back to videos, back to your notes to kind of just sort of brush up on the skills. But basically, doing exam questions is the best thing to do. Okay, so Swanwick Hall, sixth form. Hello, James. How you doing? How do I mention somebody? HKH 2008. Hello, there's quite a few people watching. Oh yeah, there's an at their name. Did it work? I think. Anyway, you'll get it in the chat. Okay, so rearrange the equation to make L over T squared the subject. Now, even if you do know nothing about pendulums, if you're in year 12 at the moment, you can do this question. So here's an equation that you've been given, and it asks you to do some manipulation to that to actually work this out. So even if you're in year 12, you can do this. There's no A-level year 13 knowledge needed at the moment. We've got a squared thing over here, so that kind of gives me a bit of a clue. And the first thing I'm going to do is square both sides to say that t squared is equal to 4 pi squared L over G. So all I've done there is square everything. Okay, and I can see a few people are kind of starting to put stuff in over there, which is great. It's quite difficult with A-level equations to put them in the kind of just a kind of text chat box, but I think people like free maths lessons are doing really well. L over T squared. So what I'm going to do is bring the G. So I guess in my head I'm bringing the G up here, and I'm bringing the 4 pi squared over there, and then I'm bringing the T squared over there. Okay, I kind of almost like just see the kind of the symbols kind of moving around. So basically that then means that we've got, I'm just going to put the equal. So we're going to bring the G up here. We're going to bring the 4 pi squared underneath. We're going to keep the L up here. We're going to bring the T squared down there. So we can say that L over T squared is equal to G over 4 pi squared. Okay, now this thing here has been done for a reason. And what you'll see is as you do more and more past exam paper questions, there's often a reason why they get you to do something like this. It's not really just testing your ability to rearrange an equation. This is a clue for something coming up later. Okay, we then have this experiment. Now, do let me know in the chat if you've actually done the kind of pendulum practical beforehand. The setup that I've got here is fairly standard. So what we have is like a pendulum bob at the bottom. We've got maybe a couple of blocks of wood, which I probably should have prepared for the live stream, but I don't actually have one with me just at the moment. But basically this means that if you clamp the 2 blocks of wood together, if you undo the clamp slightly, you can pull the string up through the middle, and that allows you really easily to adjust the length of that pendulum. The other thing is that when it actually comes to measuring the length, a lot of people find it quite difficult, and this is A-level at the moment, Sean. A lot of people find it quite difficult to put the ruler up to this and then it's kind of moving around. You can always take this out and like put it down on the desk and then measure it on the desk. So just because the pendulum is going to be going side to side, it doesn't mean that you can't unclamp it, put it on the desk, and then work out very precisely the length of that pendulum. Now, the other thing you need to know about is that the length of the pendulum is from the point that it's pivoted up here to the centre of mass of that object. So what you might want to be thinking about doing is working out maybe if it's a spherical bob at the bottom, you might measure the diameter using a micrometer, and then it might give you a reading of maybe, say, 12.0 millimetres. Okay, that means you know the radius, if that's the diameter, then the radius would be something like 6.0 millimetres. And that means you only then need to put your ruler to the end of the string, and then you just add on 6 millimetres to your measurements each time. So what I'm trying to do here is kind of talk through the practical with the kind of experimental skills that you will have developed in school that you probably remember if you're reminded, but also you could be assessed on in your exams that come up. So it's not just about the kind of easy numbers, it's about the actual experimental method. Okay, we now have a table to complete with the values of the time period for one oscillation and t squared. So always you need to make sure that you time at least 10 oscillations. If you try and like do 20 or 30, the danger is then that you're measuring such a long time that the amplitude drops to almost 0, so you can't really detect it. So about 10 is good. And all we need to do is just take this number, divide by 10, so that's 1.42 1.44 and 1.52. Okay, now the other thing is this bit down here. Does anybody in the chat, any A-level people, know what we call this kind of marker at the bottom? So if you want to put it in, if you can type it correctly, I'll be really impressed. I'm just going to have a quick sip of tea. What do we call the marker at the bottom where we're maybe recording the time from? James, great stuff. The real Jay Linton, I think you were here last night, weren't you? George, yeah. It's really difficult to read some of these. Olwyn, Nipa, yeah, so HSH, Arnie, not quite. The Lord of Moons, excellent. Riptides Kills, not quite. Sean, so it's basically a fiducial marker. Okay, and this should go at the equilibrium position. The reason for that is that the bob spends the least amount of time there, and therefore you're going to get the best estimate when you're stopping or starting and stopping that stopwatch. The problem is if you put this marker at the maximum displacement, as this swings up there, it's going to spend a lot more time here, and therefore there's going to be a greater uncertainty about when exactly you start and stop the timer. Whereas it's travelling fastest at the bottom, it spends the least amount of time there, but that means you're going to be much more certain that as it goes past that point, you've got a definite start and end point for your oscillations. So this fiducial marker should go at the equilibrium position, because that's where this pendulum spends the least amount of time. And it would be the same if you had a mass which was going up and down. Okay, so we've got the values for t. They're to 3 significant figures, like that data. We're then just going to work out t squared. So 1.26 squared would be 1.5876, that's 1.59. And basically, I'm just going to cheat a bit because I know what the answers are because I wrote the questions or put them together. We get these values here. So this is very much a simple case of just completing that data. So 3 significant figures, 3 significant figures, 3 significant figures. All good stuff. And I'm hoping that this is quite kind of easy stuff for a lot of people. And of course, even if you're in year 12, this is stuff that you can do now. There's no new physics just yet. Plot the data on the graph and calculate the gradient of the straight line. So for this, I found that pretty much everybody is really good at drawing graphs. You've done a lot of it when you've done your PAGs, and in the exam they don't want you to be spending lots of time kind of adding stuff to the axes. They just want to see that you can actually do the physics. So I'm just going to see the chat for a sec. It's just gone weird, it's just stopped. Is that working in the chat? Hello? Okay, so basically the first thing we're going to do is we're just going to plot that data. We've got t squared and length. So the length is 0.3 and this is 1.17. Oh, cool. Hello. Hello. Hello, the birds, Ryan, everybody. Yeah. Okay. How to choose the scale. For this one, for exams, they tend to give you the scale. So you don't need to worry about that. But basically you want it to be the biggest possible use of that graph paper. Okay, so I'm just going to sort of add these. So 0.35 is 1.32, 0.4 is 1.59, so it's about here. 0.45 is 1.74, 0.5 is 2.02, 2.07, and then 0.6 is 2.31. Is that right? I think that looks about right, doesn't it? Okay, so what we have is some kind of real world data. Right, so this is this a paper 3 question? This question is about simple harmonic motion, but it also involves a lot of the practical skills. So it kind of involves lots of different bits and pieces. So we've basically plotted our data. We're then going to use a pencil, a line of best fit that has a clear bit so we can see the points above and below it. And we're just going to sort of get approximately something a bit like this. So I reckon that'll do. Okay, we also need to calculate the gradient. The 1.59, 1.26. Oh yeah. Oh, have I messed that up? So yeah, that should be. Sorry, I've messed this up, Charlie. So when it's 0.4, it should be 1.59, which is here. So ignore that. And when it's 1. Is that the only one I've messed up? 1.26. I think that's all right, is it? Yeah. Okay. So yeah, that'll do. I'm just going to leave the line there. Okay. Obviously, when you're in the real exam, it's a lot more easy to concentrate. Okay. So we've got this. Now, everybody, please just do the simple things. Okay. If you have to work out a gradient, draw on a massive triangle. The amount of clever students I've seen who've just messed something up and they didn't have a gradient triangle drawn on their graph paper meant they didn't get marks when they could have got them. So we've got this. The change in y value is going to be 0.60, which is a point up here, minus 0.30. We're going to divide that by the change in x value, which is like 2.3 minus 1.15, something like that. Right, Gilby, this is a great question. How do you draw the line of best fit? First of all, they're not super picky because they realise that when you've got 20,000 students doing the exam, there's going to be some variation of where people put it. You don't have to go through the origin in this case because this isn't the origin because it's not the 0, 0 point. So we're really just looking at the data in this example. And ideally, you want to have roughly the same number of points above and below the line. So really, my line is a bit off because I plotted that in the wrong place. But if there's 6 points, you want about 3 above it and 3 below, or ideally, as many points on that line as possible. Okay, but they'll always give you like a certain degree of leniency in the exam, and also they'll make the data relatively straightforward to plot that line through. Okay, so we've got this 0.3 divided by 2.3 minus 1.15 is 0.26. So the gradient is equal to 0.26, and I reckon these points here are to 3 significant figures, really, aren't they? And that one's to 3 significant figures. So I'm going to say my gradient is 0.261. Okay, that is not the answer. Okay, that is the magnitude of the gradient, but in physics, not in maths, maths like make stuff up. In physics, where we're kind of looking at the real world, we have units. So we've got meters divided by seconds squared. So therefore, the gradient is really 0.261 meters per second squared. Okay, and I can see the real Joe Linton is rushing ahead, which is great. Okay, so we've got the gradient, okay, and in this way, we've had the length up here and the time squared on the bottom. Now, it says the gradient of the line is equal to L over t squared, because that's what we have here. We've got length divided by t squared. Now we're going to use the value for the gradient to determine the value for g from this experiment. Now, we know from the start that L over t squared is equal to g over 4 pi squared, but here it says L over t squared is the gradient. So what we can then say is that the gradient that we've calculated is equal to g over 4 pi squared. Right, Ken, excellent question. And I think, Owen, you've answered really well, yeah. So basically, are you allowed to do that? Yes, you are, and I would recommend it because that's going to give you the biggest possible triangle, which means the error that you might have in reading the points from the line of best fit are going to be the smallest percentage uncertainty. So now, it's not so much the values I've worked out. You always do it. You always draw your line to the actual points on that line. So that one there, I read it as 0.6 and 2.3, even though I plotted 2.31. And down here, I read that as 1.15, even though I plotted 1.17. So you don't draw the triangle to the points you've plotted, you draw it to the line of best fit, but do it as big as possible. Okay, coming back to this then, we know the gradient is equal to g over 4 pi squared. We want to find the value of g, so if I basically rearrange this, I can bring this up to here to say that the gradient multiplied by 4 pi squared is equal to g. Okay, now we worked out the gradient in this question as 0.261 meters per second squared. If we multiply that by 4 by pi squared, let's see what we get. Now you could use your rounded down value here. You could use the value in your calculator. To be honest, there's kind of a, depending on stuff, can we really give this to more than 3 significant figures? I don't think so. So I'm going to say 0.261 times 4 times pi squared is equal to 10.3. Now that is the answer, and that's going to be meters per second squared. Sorry, I've just been doing a GCSE paper, so I'm like GCSE thinking. So meters per second squared. That's because the units for this are meters per second squared. 4 is just a number, pi squared is just a number, and therefore the units for that are going to be the units for this. And this is kind of what we expect, because it's going to be around 9.8 or about 10. So this is a very standard, simple way of measuring the gravitational field strength using a pendulum. Okay, now looking at this, some good questions come out, which I will answer. You can do this question if you're in year 12, because it basically gives you an equation that you don't know. It asks you to do some manipulation. It then asks you to plot some data or do some kind of calculations, which are just dividing by 10 and squaring. So anybody can do that. You could give that to like a year 7 student. We then plotted some data, drew a line of best fit. That's like very much a GCSE skill. And the only bit of A-level stuff really came in at the end over here. Okay, so how do I say your name? Is it Mr. CLX6? Murlik6? Okay, basically, somebody in the chat says, for a question like this, if the exam board would tell us to calculate the absolute uncertainty, would you just do your answer minus G over G? I think at A level, if you had a paper, if you were doing like a practical, like a real exam board question, they might get you to this point, and then they might ask you to maybe look at the uncertainties. I mean, if you had, one thing you can do here is look at what we call percentage difference. Okay, so percentage difference is something that you could look at. And basically this is going to be the difference between your calculated value for that constant and the accepted true value. Okay, so the percentage difference would be equal to maybe your value minus the true value divided by the true value multiplied by 100. So in this case over here, our value, like your value that you've just worked out in the experiment, is 10.3. The true value is maybe 9.81. We're going to divide that by 9.81, and it's really the modulus of this that we're interested in, so just the positive side of this. Going to multiply that by 100, so 10.3. This is going to be equal to about 4.99, so about 5.0%. So really it's basically within plus or minus 5% of the true value, which means that this is a pretty good experiment. And I suppose then this might then lead on to looking at uncertainties. If you want to look at uncertainties in a little bit more detail, do you want me to do those in a future live stream? It's kind of like the most boring topic because it's not really interesting or exciting, but it's also quite useful. So yeah, I could maybe do that, Yusuf, Raymond, in a future live stream. I could do that. But yeah, uncertainties are quite difficult. And often what you need to do or sometimes if it's like a practical thing, is you compare maybe the percentage or the total percentage uncertainty. And what you do is you compare that to the percentage difference. And basically, if the percentage uncertainty, PU, if that's bigger than the percentage difference, then that can account for that difference, and therefore everything is good. However, if your percentage difference is bigger than the percentage uncertainties from that experiment, that means that there must be something wrong with the experimental setup that you've done, and therefore that's a bad thing. Okay, and yes, right. People are asking lots of good questions, and I do have videos, because what I do is basically make videos so that if you're not in the stream, you can find anything you want to. For example, if we go to, I'm just going to show this to you. So this is A-level physics online. If you want to find any video, all you need to do is just scroll down to the footer, and there's something here where it says full video list. If you click on that, it then has a list of all of my videos on this website. And we've got questions here on uncertainties and units. So there's something there which might be useful about, so that's quantities and units. I do have, where is it? Practical skills. Well, that's a bit annoying, isn't it? Okay, so there's practical skills here looking at uncertainties, maybe in single measurements and so on. So if you just click on that, you'll find a page. Thank you, FIFA Moments. Appreciate that. You'll basically find videos where I talk about different sorts of uncertainties and how to deal with them. And what I'm going to be doing in the future is redoing a lot of these, but that's probably more for the younger generation coming through. Yeah, the other thing I have is if you go, and this is like stuff that you can find, but it's maybe not that clear, but if you go to books, what I have are my daily workout books. If you're in year 12, this is brilliant. If you click on book 2, then what you can find on this, I've got my question index for the book. So if you have a look in the question index, what you'll see for my second daily workout book is I have lots of questions about uncertainties. So if you've been doing this, you've got questions about uncertainties here, 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 here. So basically, if you did book 2, if you're in year 12 and not sure about this, have a look at book 2 and that could really help you. And the other thing here is that if we look at the worked solutions and we look at book 2, this is just like an example of kind of what's in the book. I do have lots of questions where I talk about how to calculate uncertainties, and then I give worked examples. And so there's a huge amount of uncertainty questions. There we go. There's a question about uncertainties there, another one there. Basically, I have bits here about how to actually calculate these. Okay, right. I think we're coming up to the end of the live stream. How much do the books cost? They're only £9.99, but of course you can order them on Amazon. They'll arrive as a beautiful book, just like this. Lovely printed, lots of questions. There's basically 6 books, well there will be 6 books. Book 1, Book 2 and Book 3 are for Year 12. Book 3 is perfect for anybody in Year 12 because that will make you revise all of the core content that you've been covering this year. And that means you'll do better in your exams and get a better UCAS predicted grade. Book 4 is from the end of Year 12 and the start of Year 13. And I haven't finished Books 5 and 6 yet. And I do videos on everything. Right. Thank you, everybody. I hope all of you are doing all right. That's the end of the live stream, but I'm going to have exam revision live streams in the evenings from 7:30 till 8:30, and they're going to be basically Sunday night, Monday night, Tuesday night, Wednesday night and Thursday night between now and your exam. So basically I'm going to be your other teacher and hopefully get you through stuff. So if you haven't seen the whole stream, you can obviously just join again, and I'll put the link up on YouTube probably in the morning once it's all finished processing. Thank you, everybody, and good night. I hope all of you have a good evening, and I shall see you again tomorrow.